Hi everyone! Today's lecture covers EEG signal processing techniques. One of the critical steps in the design of brain-computer interface or BCI applications based on electroencephalography is to process and analyze such signals in real time in order to identify the mental state of the user. These signals are noisy, non-stationary, complex, and of high dimensionality. Therefore, mental state recognition from EEG signals requires specific signal processing and machine learning tools once you have acquired the signal. Today we're going to learn about how to do EEG signal processing and the kind of algorithms to use to do that. The first step is called feature extraction, describing the EEG signals by a few relevant values called features. Such features should capture the information embedded in the EEG signals that is relevant to describe the mental states to identify, while rejecting the noise and other non-relevant information. The second step, denoted as classification, assigns a class to a set of features extracted from the signals. This class corresponds to the kind of mental state identified. Finally, the result can be translated into a command to control a device, or maybe to the word that describes the mental state of the person. As an example, let us consider a motor imagery-based BCI. In this case, the two mental states to identify are imagine left hand movement on one side and imagine right hand movement on the other side. To identify them from EEG signals, typical features are band power features. For example, the power of the EEG signal in a specific frequency band. For motor imagery, band power features are usually extracted in the alpha frequency band, which is about 8 to 12 Hz, and the beta frequency band, which is about 16 to 24 or 30 Hz. It depends on the application. For electrodes localized over the motor cortex areas of the brain around locations C3 and C4 for right and left hand movements respectively. The general process to determine the final computation of the pattern recognition or classification in EEG signals is going to be presented right now. On your right, we're going to see as the first step the signal recorded during left or right hand motor imagery, and then band power in the alpha and beta extracted from electrodes located over the motor cortex. Then classification occurs once a linear discriminant analysis was performed, and finally we can estimate which class belongs to left or right hand movement. With BCI, there are three main sources of information that can be used to extract features from EEG signals. We can get the spectral information. Such features will describe how the power in some relevant frequency bands varies. In practice, this means that the features will use the power in some specific frequency bands. We can also get the temporal information. In this case, such features will describe how the relevant signal varies with time. This means using the EEG signals values at different time points or in different time windows. And we can also get the spatial information. Such features will describe where the relevant signal comes from. This means selecting specific EEG channels or focusing more on specific channels than on some other. BCI based on oscillatory activity such motor imagery mostly needs and uses the spectral and spatial information. We're going to talk more about the spectral methods. The most common methods used in spectral analysis are divided into two categories: frequency domain analysis and time frequency domain analysis. In frequency domain analysis, we estimate the spectral power of stationary signals, whereas in time frequency domain is related to the localization of both power and in time and frequency. Methods in frequency domain include the fast Fourier Transform and the power spectral density or PSD. In time frequency domain, one of the most common methods is the Wavelet transform. Okay, now let's first talk about the frequency domain analysis. The Fourier Transform is a tool that breaks a waveform into an alternate representation characterized by sines and cosines. The Fourier Transforms show only that any waveform can be rewritten as a sum of sinusoidal functions. Notice that the Fourier Transform is just an integral transform. The Fourier Transform changes the signal from the time domain to the frequency domain and back again if needed. And we're going to use the computer to take some samples. So the Fourier Transform is going to be converted into the discrete Fourier Transform now. The discrete Fourier Transform, or DFT, is the equivalent of the continuous Fourier Transform from signals known only at a specific instance. First of all, I would like to thank this guy for the incredible explanation about the DFT. I'm sharing his webpage for future reading. And let me describe the discrete Fourier Transform as let's say xk, capital XK, is the DFT of xn, which is the sequence, and it is equals to the sum from n equals to 0 to n equals to the number of samples minus 1 of the n sample of our input signal multiplied by this complex exponential, which is e to the minus I times the rate of the complex sinusoid of 2p radians times k, which is the frequency at that moment, times n, which is the present sample number. All of these over n, which is the number of samples in our input signal. Notice that each time domain sample is multiplied by a complex number. This calculation can be achieved with a very simple function, as can be seen here. Notice that this function takes as an argument an array of complex time domain samples and returns an array of spectrum data with the same number of elements as a time domain dataset. Each element of the spectrum dataset corresponds to particular frequency related by the frequency resolution of the sample set. While talking more about the frequency resolution, while the array returned from the Fourier Transform function is useful, it doesn't directly contain all the information that will be required to determine the actual response of a given signal. One factor to consider during the development of the Fourier Transform function is the frequency resolution of such transformation. The frequency resolution is calculated as sample rate over the number of samples of the data set. Given the array output from a Fourier Transform function, the frequency corresponding to each value in that array can be calculated as n times the frequency resolution, which is fr. Now that we know what the DFT is, let me describe the fast Fourier Transform. The fast Fourier Transform is a fast computation algorithm for discrete Fourier Transform. Recall that the DFT is defined as the sum from n equals to 0 to n minus 1 of xn times the complex exponential e to the minus I times 2p over n, which is called the twiddle factor, and is labeled as Wn, which is the same value as I described before. The DFT can be exploited by using separate sums for even and odd index values of n. This is what we call the Cooley-Tukey algorithm. We have the even terms and the plus the odd terms. So as a result, that will be our resulting sum. Let me describe this with an example. We're going to take the even index terms of the input signal. We take the, let me see, for instance, we have x of 0, x of 2, x4, and so on. And then we take the n over 2 points of the DFT to get the output as x, e, 0, and so on. Now we have the odd index terms of the input signal. We take the n over 2 points of the DFT to get the output as x00, x01, and so on. We have to combine all these values to get the DFT of the whole sequence. We're going to take xe0 times 1. Why? Because the arrows indicate multipliers, plus x0 times w8 raised to the 0 power, notice here. That will get me x0, and suddenly I will work down here. I will get x1 has xe1, the first coefficient of the even term, plus w8 raised to the first power times the first coefficient of the odd term. The algorithm reorders the time domain samples and uses a divide and conquer approach to reduce the number of operations required to calculate the spectral information. As a basic implementation, I'm going to describe this with a basic function that takes the FFT of the input signal using C#. To begin, a function must be defined because this function will be used in a recursive fashion when rearranging the time domain samples. A check must be put in place to verify the size of the array being passed is greater than 1. If it is equals to 1, only that value should be returned. The next step is to initialize these arrays and populate them with the correct values. Then calculate the Fourier transform of these arrays. This accomplished with a simple loop. By calling the FFT function recursively, the amount of code required to develop this algorithm can be minimized. The next step is to multiply each element of the odd Fourier transform array with its corresponding complex number. This is accomplished with a simple loop. The final step in this process is to carry out the addition and subtraction of each of these values. In this step, for values of n between 0 and n over 2 minus 1, each even value is added to each odd value. For values between n over 2 and n minus 1, each odd value is subtracted from each even value. The final loop to accomplish these calculations and return the final array containing the Fourier transform is shown here. This resulting array X holds the spectrum information of the given signal. This information is subject to the same frequency resolution as in the DFT. Now, the power spectrum density. Well, the power spectrum density, or PSD, shows the strength of the variations as a function of frequency. The unit of PSD is energy per frequency. It is useful to represent the PSD in the logarithm unit decibels relative to 1 Hz. So how power spectral density can be computed from the FFT? Well, let me give you an example with a very basic implementation of this. First, we take the length of the sequence as a sample number. Then we get the FFT of the signal. In order to get the PSD, we just need to obtain the absolute square values of the FFT output. Then the frequency range becomes from 0 in steps of 2 pi over n up to 2 pi minus 2 pi over n. Finally, we can plot the results with respect to frequency. The PSD can be expressed by using a logarithm scale in decibels for better understanding. Now let's talk about the time frequency domain analysis. The most common method in the time frequency domain analysis is called the Wavelet transform. Modern wavelets are nothing but transformation functions. I can say that they are used as a template. The name wavelet because they're baby waves, oscillatory functions. The name mother is because they form the basis of Fourier transformation process. The entire notion of wavelets emerged as an alternative to Fourier transform because of the time-frequency resolution problem. The Fourier transform says what frequency components appear in the signal, but is unable to tell at what exact frequency occur at what time instances. So, imagine a mother wavelet has a window function that moves or shifts along the time series signal from time t equals to 0 to time equals t. The portion of the signal in that window is multiplied by the mother wavelet and then integrated over all times to get the wavelet coefficients. So the general procedure starts with taking the wavelet and compare it to the section at the start of this original signal. Then calculate a correlation coefficient C, which I'm going to describe this in a few moments. The width of the window is technically called the support of the window. Then shift the wavelet to the right and repeat the step until the whole signal is covered. You need to repeat the process by shifting the wavelet to the right until the whole signal is covered, and so on. How to make wavelets? Well, the most basic wavelet that we can use and compute is called the Wavelet wavelet. To make a Wavelet wavelet, you just need to create a sound wave first, then create a Gaussian with using this formula, and multiply them point by point. And yay, you have now the first wavelet. The sine wave and the Gaussian must have the same number of time points and the same sampling rate. The frequency of the wavelet is the frequency of the sine wave. Similar to the way a Fourier transform uses many waves of different frequencies, time frequency decomposition via wavelet convolution involves using many wavelets of different frequencies. Unlike Fourier analysis, however, the frequencies of the wavelet can be specified by you rather than being specified by the number of data points in the time series. You can use as many wavelets as you want. There are several types of wavelets as shown here. We have Davis's, Morlet, as described before, hey, the Mexican hat, and Mayer, and so on. We have a lot of wavelets. Why wavelets? Well, we can use wavelet convolution as bandpass filters. Yay! So there is no need to design a bandpass filter in a specific way. We can use them as bandpass filters. Convolution can be interpreted as a vector that expresses the time-varying mapping between a kernel and a signal. Here, the wavelet and the EEG data. Let me first explain how to interpret this. In this figure, we can see a row of EEG data, which I call the unfiltered time series. The wavelet convolution can act as a bandpass filter. In this picture, we can see the power spectrum of the Wavelet wavelet and the EEG data. Note that the wavelet has a Gaussian shape in the frequency domain. In your right, we can see a plot with a point-by-point multiplication of the frequency spectra of the wavelet and the EEG data. Now, this picture presents the result of the convolution overlaid on the top of the original EEG data. This figure also illustrates how the result of convolution reflects activity that is maximal at the peak frequency of the wavelet. Wavelet transform allows the use of variable size windows. In order to get high frequency information, short time windows are used. Let me explain this picture by saying that xn is the raw of EEG data, and each step contains two digital filters, Gn and Hn. Gn is a high-pass filter in nature, while its mirror image Hn is a low-pass filter in nature. We also have two downsample other wavelets. Each stage outputs provides a detail of the signal D and an approximation of the signal A, where the latest becomes an input for the next step. The number of levels to which the wavelet decomposes is chosen depending on the component of the EEG data with dominant frequency. A good example on how to use Wavelet transform as bandpass filters in EEG feature extraction can be seen here. Wavelet transforms divide EEG signal into small segments. Each segment is taken as a frequency band. That segment of frequency band can be considered as stationary signal. The discrete wavelet transform divides the signal at different frequency band by decomposing signal into detail and approximation coefficient information, passing through high pass and low pass filters. We can see at first level D1, the majority of noises were present, 25 to 50 hertz, which is a gamma band. And the rest, 0 to 50 hertz, they're going to be filtered again in the second step. In the second level of decomposition, now we get beta frequency band, which is 12 to 25 hertz, and the approximation coefficient corresponds to frequency bands from 0 to 25 hertz, which are going to be filtered again in another level, which is level 3. In the third level of the composition, now we get 0 to 12 hertz because we're going to get the alpha frequency band, which is 6 to 12 hertz. Then the approximation coefficient is going to be filtered again to obtain theta frequency band. And the rest, the final approximation coefficient is just the delta frequency band, which is from 0 to 3 hertz. Notice that on each level of the composition, the detail coefficients corresponds to the frequency range, and the rest, the last approximation coefficient is just the last frequency band that we're going to describe. Well, that's all for now. Thanks for watching.